Hi everyone, I'm Laurynas Lukas Kanopka, and I'm here with Olivia Caruso and Rafael Munoz Gonzalez, and this is our STA4211 final project on season and carrier effects on U.S. domestic air travel demand. So, we were very interested in finding out the best time to travel at airports and if there was any way around the seasonal traffic that we see during breaks and other peak seasons. We used a two-factor factorial experiment using a randomized complete block design to see what really drives passenger volume. So, let's start off with covering the motivation for our experiment. I'm from out of state, and every single winter I fly home to Chicago O'Hare, also known as ORD, through Orlando, aka MCO. And if you've ever flown through O'Hare or Orlando, or any large airport for that matter, in December near the holidays, you know that it's chaos. It feels like the entire world is packed into one terminal. Flights get delayed or canceled. The lines to check in are long. The lines through TSA are even longer. And honestly, I just don't have a lot of fun trying to get through all of this. So that brought us to the question, is it just the legacy airlines like United or American that are packed? Would it be less chaotic if I flew a budget carrier like Spirit or Southwest? So these questions led us to our main research question. Does the seasonal surge we feel in winter affect all airline types equally, or is there a difference? So, to answer this, we looked at 2024 passenger data from the Bureau of Transportation Statistics. This seemed like a fair and accurate source to pull from. We explicitly chose to look at only a single year because adding multiple years would introduce too much historical noise, especially with post-COVID recovery trends still fluctuating in the previous years. So, sticking to 2024 allowed us to isolate the seasonal interaction without worrying about the COVID recovery or any other events from previous years that may skew our data. So, for factor A, we looked at season and we looked at fall, winter, spring, and summer. For factor B, we looked at carrier type and we grouped airlines into legacy, like Delta and United, and low-cost carriers, like Southwest and Spirit. And then we blocked by airport. So we know an airport like Atlanta is way busier than most other airports. So by blocking on six major hubs, including O'Hare, Atlanta, and Orlando, we removed that variability so we could focus purely on the effects of season and carrier.
Okay, so now let's look at how we modeled this. Because passenger counts are naturally skewed, you can't have negative passengers, and the volume differences are huge. We performed a log transformation on the data. On this slide, you can see our standard ANOVA model for the randomized complete block design. So our fixed effects are season, which is represented by tau, our carrier type, which is represented by beta, and then our interaction effect, this is our interaction effect, which is represented by the tau beta term. Then, of course, our block effect is represented by rho. And this accounts for the fact that O'Hare and Orlando have naturally different baseline traffic levels compared to others. Before we ran our formal tests, we looked at an interaction plot. So on this interaction plot, the x-axis we have is our seasons, and then the y-axis is our mean passengers per volume. The top line represents our legacy carriers, and our bottom line represents our low-cost carriers. So the first thing that you can notice is that our lines are essentially parallel. So unlike our previous expectations, both lines are relatively flat across the board. Parallel lines usually mean that there is no interaction, and it looks like that both types of airlines experience that exact trend. So now we look at our ANOVA results, and they confirm exactly what we found. So when we look at our origin or our block effect, the p-value is roughly 0.057. Comparing this to our alpha level of 0.05, this is not significant. However, if you look at the mean squared column, the variance for origin is nearly double the residual mean squared. So this suggests that blocking was still effective. Looking at our season effect, we see the p-value of 0.859. This is higher than our alpha level of 0.05. So this definitely means that we have no statistical evidence that passenger volume differs based on time of year. Then we look at our carrier type. Our p-value is near to zero. So our f-value is over 30. So this means that we have significant evidence that our legacy and low-cost carriers are highly different. And then our interaction term, the p-value is 0.997, which is very close to 1. This means that there's almost absolutely no evidence of an interaction. The seasonal trends affect both carrier types in the exact same way. This is also in line with our interaction plot, showing that roughly parallel lines means that there's no interaction.
All right, so what do these results actually mean in the real world context? Well, first, we observe that the carrier effect is massive. Like, even after controlling for the season and the specific airport, legacy carriers are moving around 4 times the volume of the low cost carriers. Low cost carriers represent only about 25 to 30% of the legacy volume. And then, secondly, looking at these seasons, this was a big surprise. Like statistically, the volume is consistent the whole year round. But despite the feeling of chaos in the winter, like the actual passenger count is statistically the same as in any other season, summer, spring, or fall. So the capacity is steady throughout the year. And of course, we could not trust any of these p-values if our model assumptions fail. So we have to check our residuals using base bar plots. So on the left here, we can see a normal QQ plot, which shows the points following the reference line pretty well. So we can see that they do start to stray away a little bit at the extreme tails of the plot, which is common for a lot of real world data. But overall, I mean, the normality assumption definitely holds. And on the right, we can see that with the residuals versus the fitted values on that plot, it shows a random scatter. And we don't see any megaphone or funnel shapes. So our assumptions for the constant variance is also satisfied, and that gives us the confidence that our log transformed ANOVA model was appropriate.
Okay, so to wrap this up, what did we learn? Firstly, we saw parallel trends. So the seasonal waves hit everyone equally, and whether you fly Delta or Spirit, all of the demand curves look the same. So there's no getting around that. There's no carrier you can pick that's going to make your travel easier. And we also saw no seasonality, surprisingly. So since the season effect wasn't significant, we didn't run a Tukey post hoc test, and the data basically says that there is no significant difference between winter, spring, summer, or fall. And I was really surprised by this because my personal intuition was wrong on this sense. Winter feels chaotic due to the bad weather, all of the holidays that come in here, like Thanksgiving, New Year's, Christmas. But in terms of raw passenger numbers, it's actually consistent with the rest of the year. So, in conclusion, our study showed that while legacy carriers dominate the market share, the ebb and flow of passengers is a universal trend across the industry. And for everyone planning to travel, just know that the busy season is busy for everyone. There's no way you can game the system and pick a different carrier and have an easier or harder time for that matter. So, that's all we have. And thank you so much for listening and thank you for your time.